Nuclear reactor power density. Control of the nuclear plant, Part 2. Nuclear reactor power density. Before we discuss the subject of reactor control and operation, it is desirable to examine some of the spatial and temporal power density variations which may occur in a reactor core. It has been shown that for a cylindrical core, the thermal neutron flux follows a cosine shape in the axial direction and a Bessel function shape in the radial direction. Request: it is hoped that this session is going to be useful to you. Please press like. Please subscribe. We know both of these functions are highly peaked in the center and approach zero near the edge of the core. Since the power density is directly proportional to the thermal neutron flux, the central fuel bundle will under such conditions operate at a substantially higher power output than the average fuel bundle. This condition is clearly undesirable since the total reactor output is now governed by the power rating of the central bundle only. A more uniform power density throughout the reactor volume is clearly desirable. A more uniform power density can be achieved in a reactor by: first, the judicious use of neutron absorbing materials called absorber rods. Second, the use of materials which are rich in fissile nuclei and called booster rods. And third, by appropriate management of the refueling process. For example, in regions where it is desirable to depress the neutron flux, hence lower the power density, neutron absorber rod or depleted fuel could be placed. The effect on reactor power is that it can generally be doubled without an increase in the central fuel bundle power output. Figure in next slide provides a graphical comparison of a flattened with a non-flattened thermal neutron flux. Comparison between a peaked neutron flux associated with a homogeneous core and a flattened flux obtained by the suitable use of flux flattening option. Xenon poisoning. We discuss the role of xenon poisoning and the need for sufficient excess reactivity to overcome its poisoning effect during reactor operation and start up. One additional important effect associated with xenon is that of spatial stability and the attendant possibility of inducing significant power density oscillations in the core. Indeed, one function of the control system of a reactor is that of suppressing such spatial oscillations, which affects all large thermal reactors. This is a very important phenomena in large thermal reactors, but for present we shall not discuss it in detail here. Request: it is hoped that this session was useful to you. Please press like. Please subscribe.